My name is Jim Trudeau. I'm a Senior Applications Engineer here at Cypress. Today we're going to be working with a particular starter kit. This is the S6E2GM starter kit, and it has an FM4 part. And what we're going to do is we're going to drive a very simple little DC motor using a very complicated peripheral. And in this video I'd like to accomplish a couple of things. Introduce you to the multifunction timer peripheral and what it's capable of, and then show you for real a simple project that drives this DC motor. The multifunction timer, as I said, is a complicated peripheral. It's actually a set of 5 sub-peripherals, and the first of them is the free run timer. The free run timer sends a timing signal to all the other peripherals that are involved, and the purpose of this multifunction timer is motor control. It's really for driving motors. In addition to the free run timer, there is an output compare unit. So in its simplest form, you set a value in the compare unit and it compares itself against the timer, and that's what creates a PWM duty cycle. Downstream from the OCU is the waveform generator. If we were driving a complex 3-phase motor, we would want to generate the waveforms for the signal that's driving the motor, and that generates those waveforms based on how you set up the FRT and the OCU. In addition, the multifunction timer has an input capture unit. The input capture unit is designed to receive signals from the outside world. You might have an on-off switch, for example, and you can use the input capture unit to read the signal from those pins and control the motor. And finally, the 5th peripheral that's involved in the multifunction timer is called the ADC Start Compare. A complex motor has sensors in it, and a sensor signal, being analog, is converted by the ADC into digital values so that you can process them. To do that, it has to be done in very close synchrony with the motor. And so the same timer, the free run timer that drives the output compare unit, the waveform generator, drives the ADC. And so the conversion process is controlled by that timer and happens at the right time. As a unit, the FRT, the OCU, and the other components make a very complicated part. And what we're going to do today is something very simple. We're going to use a single timer, there are 3, and we're going to use a single OCU channel, there are 6, and that's it. So you can see that by mixing and matching these components and peripherals together, you get a lot of power and a lot of capability. So we're going to do this for real, and I'm going to walk you through some code. As a brief reintroduction to the PDL, if you haven't seen the other videos in the series, to use the PDL, you need to configure it. You need to configure the peripheral, and you do that by setting fields in a configuration structure. You need to initialize the peripheral, and you do that by making a PDL function call. Once it's initialized with the information that you set up in the configuration structure, you then enable or start it, and then you use the peripheral. You make function calls. So you can scan, transmit, receive data, clear and interrupt, whatever is required. And there's an API function call that does that for you. So I've built a project. I built this project from scratch from the PDL devices folder. In the PDL, there's a devices folder, and another video in this series shows you how to create a custom project using the information that's in the devices folder. So let's take a look at this project for real. I've built this project, added in the necessary source files, and PDL user.h, which you use to configure the entire PDL. So let's take a look at that first. That's where we begin. So here's the PDL user.h file. I'm going to be using a couple of peripherals. I'm going to use an analog to digital converter. On this particular board, there's a light sensor, and we're going to use the light sensor as our signal source to control the speed of the motor. So since I'm using an ADC, I need to enable it. And in PDL user.h is a long list of every single feature that's in the PDL, and I need to turn it on. So I have set PDL peripheral enable ADC 0, because that's the one I'm using, to on. I also need an MFT. So let's scroll down the page to the multifunction timer interfaces. This particular part supports 2 separate MFTs. Each MFT is capable of driving a 3-phase motor, so this part could drive 2 3-phase motors. We're doing a simple little DC motor, but I need to turn it on. I'm not using MFT 0, I am using MFT1, and you can see that that's on. And the MFT1, I'm using two parts of it, the FRT and MFT OCU. The reason I'm using one is practical. That's the way this board is wired. We have a board we're going to use an Arduino Shield, and it is the MFT1 interface that is wired to the Arduino Shield. So that's what controls my choice. Notice that I am not using the waveform generator or the capture unit, the input capture unit, or the start the ADC. This is a very simple demo, but this peripheral has a huge amount of capability. Okay, let's take a look at the code. I've written that in main.c. We have some board-specific defines. So for example, the input channel. The light sensor is on analog channel 17. I know that by looking at the schematic. And I'm using MFT1 for the OCU, and I'm going to be using OCU channel 4. And again, the reason these things have been selected by me is because that's how this board is wired. In other videos in this series, we talked about how you use the PDL. You need to configure it, initialize it, start it, and use it. So here's the code that sets up the ADC. We declare a couple of configuration structures that are required. One is for the ADC itself, and the other is for the scan process. And then we have a PDL macro to zero out those structures, so we're starting with a fresh slate. That's good programming practice. And then we set up the scan. And the scan is going to use channel 17. We're going to do a single conversion. We're not going to do repeat conversions because we're going to start this ourselves using software rather than an interrupt. We're not using a timer, and that pretty much sets up the scan. The ADC itself has a series of things that we set. For example, we're going to use least significant bit alignment, and we're going to set the timer values for generating a hertz rate for the sampling. So we get a certain number of samples per second. Then we do the same thing for the MFT peripherals. Remember, this is really a collection of 5, we'll call them sub-peripherals, but they're 5 peripherals that all work together to drive a motor. And as I said, we're using 2. We're using an FRT, so I've got a structure for the FRT, and we're using the OCU. So I have a structure to configure the OCU. We zero those out, and then we configure them. For example, the timer can operate in 2 modes. It can count up and then back down to 0, or it can count up and immediately go back to 0 and count up again. So the timer can work in one of 2 modes. It can count up and down, so it counts up to a maximum value and then back down to 0, or it can count up, reset to 0, and count up again. We're using up-down count. And then we do some math to set the clock to the right hertz rate so that just sort of ad hoc playing around with the motor came to the conclusion that we really wanted to have about 500 hertz. So we did the math to set up the count cycle to generate about 500 hertz. Then we configure the OCU. We have to have a timer signal that drives the OCU. And we're using FRT0. So we connect FRT0 to the OCU. All of the peripherals involved in the multifunction timer work together like that. Once we finish setting it up, then we initialize it. So remember, configure, initialize, and then you can start it up. The OCU has a compare value, and we make a function call to set the initial value for the compare, and that will decide what the duty cycle for the motor is. And when we're done, we enable it, and then we start the timer, and that starts everything. The OCU is tied to the timer. Once the timer is running, the OCU is running, and we're good. There's some additional code in here that controls the pins that the motor is wired to. So this is hardware specific and based on the board that we're using, the FM4 starter kit. So we have a couple of lines that set the pins that will stop the motor and a couple of lines that set the pin that run the motor. And the other thing I set this up to do is so that we can actually turn the motor off if we want. So we set up the user button. And there's some logic to control that. So let's look at the control code. This is the main function. We set up a couple of variables that we need to run this code. So we declare some variables that we're going to need. The ADC puts data in a buffer. It's a FIFO buffer. So we've got a variable named FIFO. And that isn't actually the scan result. That's 32 bits of data, and the scan result is 12 bits within that 32 bits. So we have a variable to hold the scan result. And then we need to convert that scan result to a different number that makes sense for driving the duty cycle of the motor. So we have the compare value. So the very first thing we do is we do some GPIO setup, And then we set up the PDL. So we call setup ADC, and that sets up, configures, and initializes and enables the ADC. And then we call setup MFT, and that runs all the code to configure, initialize, and start the MFT. Then we start the motor spinning. Once the motor is spinning, then it's time to do some work. And we have a main loop, and the first thing we do is we trigger a scan. Then we wait till it's done. So as long as it's still busy, we do nothing, we just spin. And then when it's done, we get the data. So we call read scan FIFO. These are all PDL function calls. And then once we get the 32-bit value, we pull the scan result out of that. Then we transform that scan result, which is a range from about 0 to 4096, 12-bit value, and we change that into something that makes sense for the OCU. Finally, we write the new compare value. So as the signal from the ADC goes up and down, the compare value will go up and down and change the speed of the motor. And then we check to see whether someone's pressed the button, and if they have, we toggle the motor from stopping and starting. So let's see how it all works. We will click the debug button, we'll download the code, which of course takes a minute. And here we are stopped at the first line of main. All right, let's see this thing run. We'll click the go button. And I'm not sure if you can hear it, but the motor is running. It's being driven by a light sensor, and the light sensor is actually under the board. So I'm going to shine a light. And now that motor is really humming. And if I take the light away, it slows down. And I can stop it. Okay, so that's a fairly simple demonstration of motor control, but why would you really want to do that? Well, I suppose you could, on a sunny day your fan would go faster, which might be fun. But really what we're talking about here is feedback into a motor control system from sensors. And those sensors are being driven by an ADC that gives the necessary information into the motor control logic so that it can control the speed of the motor, the direction of the motor, and anything else that's necessary for driving the system. In the real world, with a BLDC or a three-phase motor, your code's going to be a lot more complex. But what we've shown you here is that you use the PDL to control all of the configuration that's required and then to drive the peripheral as you need to in your application. And you can do that not just for motor control, but for a whole range of peripherals that are supported by the FM family. How do you learn how to do this? You do this with the documentation. The Peripheral Driver Library 2.1 comes with complete documentation for every driver that gives you the information that you need on the peripheral itself, on the macros, on the functions, on the constants, on the data structures, all of the deep, dark details that you need to drive the peripheral or to use the peripheral. All of the deep information that you need to use the peripheral is here in the documentation. Writing code for a microcontroller may not be easy, but the PDL sure makes it easier. And to learn more, visit Cypress.com. Thanks for watching.